My name is John Delaney, and thank you very much for coming. If you have come again, I thank you especially, since I think I talked all of you into a hole last time. I talked almost 2 hours, and I will try not to do... Gee whiz. Well, let's see. When do you have to be home? Tonight's talk has some overlaps with what I've done before, particularly last time, but it'll be in some of the elements that you saw last time were sort of in the context of the technological capabilities that we're putting together to study the ocean. This will be more in the lines of a very focused effort to look specifically at a particular kind of seafloor oceanography, one that I've spent quite a bit of my lifetime studying. My colleague Deborah Kelly here in the audience has contributed substantially to the materials that I will share with you, and I would ask once again, as you will see, for an early round of applause for both Deb and for Mark Stormer, who is truly a remarkably capable professional illustrator. Mark is just a remarkable fellow, and both of the two of them have contributed very substantially to this presentation. If you would. I have here in front of me on the left a large rock that came from the seafloor, along with about 18,000 pounds of additional rock. And I'll talk about that as well. This is a large piece of a black smoker chimney. I'll talk about that. This is part of a series of lectures. These are the first two lectures and the dates, and this is today. It's a very exciting thing to talk about a new discovery, which is well within the lifetime of 98% of you. The first discovery of submarine hydrothermal vents took place in 1977. Before that, we thought the deep sea floor was, I won't say boring, because there are maybe the odd benthic oceanographer here, bottom people who study the sea floor, but all of a sudden it became very, very exciting, and I'll share that with you. The next one is going to be a much different kind of situation, and John Barros, a colleague of mine whom I will introduce you to in this lecture. He's not here today, but I'll introduce you anyway. And we will talk broadly about the implications of what we've discovered under the ocean with regard to planets, life inside this planet, deep inside this planet, like in the rocks, and life beyond Earth. We'll talk about that. And then in November, I'll be at sea with many of my colleagues from mid-July to early October, and then I'd like to come back and talk to you about what we have done with a very substantial amount of your tax dollars in terms of building a novel next-generation approach to studying oceans, which you heard a little bit about last time. What you're looking at is, again, Mark Stormer's craft here, and he shows through the water an underwater volcano. We'll explore this just a little bit. So submarine volcanism and overview. Now, a little of this might be repetitious, and some of it may be material you all know, but I didn't want to assume it a priori, so I'm giving you a little bit of background. What you're looking at in terms of the cloud cover here is actually taken from a picture of an erupting underwater volcano. And what's turning in front of you is actually a mock-up Earth with seamounts on it. Now, I've showed you this before, but I want to emphasize this is really quite profound to have a picture of your planet in which the very youngest rocks, the orange-reddish zone, are shown juxtaposed against everything else. And the Midocean Ridge, which is what is in orange, is about 70,000 kilometers long. It's the largest single feature on the planet. It is a mountain range that is actually a volcanic range that is constantly erupting somewhere all the time, somewhere. In the Mid-Atlantic Ridge, which looks like a zipper down the middle of the Atlantic, it is exactly what it is. The seafloor is pulling apart at about 3 to 4 centimeters a year. Over near, off the west coast of South America, near Easter Island, the East Pacific Rise, one's a ridge, the other's a rise, they're both the same thing. It's called the Midocean Ridge system. But that portion around the Easter Island area is spreading at about 16 to 18 centimeters a year, and it's birthing a few small plates as it goes. And so it's really pretty fascinating. That means in what, 16 centimeters a year, that means in about 6 or 7 years you've created a meter of new seafloor along a line that's at least 3,000 or 4,000 kilometers long. So it's a dynamic system. You think of plate tectonics as being a big yawn because, it goes at 3, 4, 6 centimeters a year. But it's not really during magnitude 9 earthquakes. It's really much more interesting when things happen. And what I'm telling you is that things really do happen on the seafloor on a regular basis. So you have a chance to look at that. The main point I want to make here, though, is that all of the seafloor and the oceanic crust is about 5 kilometers thick. The oceanic crust is 5 kilometers thick. The seafloor is the surface of that layer cake. And below that is what we call the mantle. And all of the lava that comes out at the ridges comes from within the mantle, sort of flows up around the crystals that aren't melted, but the melt comes up and collects under the ridges. And then as the plates spread, it solidifies and creates a layer that's about 5 to 6 kilometers thick. So that's the cake. And here are the plates. And you can see that where the plates come apart, particularly the Nazca Plate and the Antarctic Plate and the Pacific Plate, that's where this very vigorous spreading center is. That's where volcanic activity that is basaltic, very similar to Hawaii and Iceland, that's where it happens. In fact, Iceland is on top of this system. Very interesting place to go and visit in the summer. Now, there's icing on this cake, which is really equally exciting for some of us. But here are the tectonic plates. And you'll notice, I just want to bring to your attention that cute little red one up in the upper left-hand corner there. We'll be back to see that. That's in your neighborhood. That's your backyard plate. And here's what I was talking about. This is the icing on the sea floor crustal cake, if you will. The seamounts, there's tens and tens of thousands of seamounts, and they have been generated over the past 200 million years. One thing I forgot to mention to you, I won't take you back now, but the sea floor is oldest in the Western Pacific, just before the plate plunges beneath Japan. It's 200 million years old. And all of these volcanoes that you're seeing are less than 200 million years old. In fact, many of them are formed right near the ridge crest where it's spreading. Now that makes, if the geologist in you would say, oh, is that because that's where the magma is? And the answer is, of course, yes. That's not where all of them are. You see, Hawaii does not have a spreading center. It's got what we call a hot spot, deep in the earth, hundreds and hundreds of kilometers deep. There's some anomaly, chemical and maybe thermal, that has produced the Hawaii seamount chain, which you can see walking off like a picket fence there. That's been going on for about 165 million years. So it's been around a while. But mostly, many of the seamount chains you see originate at the ridge crest, and you can see that a little better here. You can see where the Nazca Plate is on your right. The spreading center is right down through here. It's not quite as brightly lit, but there's the Nazca Plate. This is all the Pacific Plate, which is obviously the biggest plate on the planet and has most of the seamounts. There are, however, a few seamounts, cute little ones in New England up here. Nobody takes them very seriously, but, and then we have our own backyard seamounts off of the Juan de Fuca, but it's a small world compared to the Pacific Plate as well. The Pacific plate is where it's happening. I mean, bottom line, the Pacific Ocean is in fact the ocean, and the Atlantic and the Indian Ocean are kind of back bays, if you really want. But the ocean is the Pacific. And make no mistake about that. If somebody stops you on the street and asks you that, just put them in their place. So what happens when a seamount moves off axis? Well, sediments build up around it. They don't necessarily land very effectively on it because just like Mount Rainier always has winds moving back and forth across it, so seamounts have currents, and they keep them fairly clean, but the sediments collect between the seamounts. And that creates a really interesting situation, which you probably haven't thought much about. As you get well away from the ridge, there's a lot of sediment around the seamounts, but the seamounts are made up of basaltic chunks of what we call pillow basalt. It's like a gigantic box full of basketballs, meaning that it's fairly porous. Fluid can flow through them. So the seamounts represent chimneys from the deeper part of the crust, and the lithosphere, which is the whole, the part below the crust, is called the asthenosphere, which means it flows while it's still solid. But it has a lot of heat left in it, and a lot of that heat percolates out in form of water, convective water, up through the seamounts. So the seamounts are chimneys. So what I showed you before, the tens of thousands of seamounts were all chimneys through the sediment that covers the seafloor. So as a result, seamounts often have hydrothermal systems on top of them, and that makes them more interesting to some geologists. All right. Now, I showed you this before, but I'm going to use it as a launch point. I showed you the earthquakes around the Pacific, and you can watch, and I want you to look for a pattern. Are the earthquakes getting more frequent? This is a period from 1970 to 2010, and you'll notice that right around 2004, in the Banda Aceh area, you'll see a large earthquake. Boom. And then Chile, boom. And I have not yet put on Tohoku, but I should. Now let's jump past that. In the Western Pacific, there is a seamount chain. It's much more complicated than that, but there is a seamount there called West Mata Volcano. And West Mata Volcano was caught erupting about 10 years ago by some colleagues at NOAA. And it was really quite powerful. There were large explosions, which were, we think, gases of hydrogen that were simply released as bubbles, and they were ignited, and when they came into oxygen-rich seawater, they simply blew up. And it was pretty energetic. But nobody knew it was happening, and when they got in too close, they began to worry about either losing the ROV that they were using. They didn't use the submersible there, for obvious reasons. And there's an old story that probably some of you have heard about. Shortly after the Second World War, there were some Japanese folks in the Western Pacific, scientists, who went out to examine an erupting volcano in the Marianas Arc. And as luck would have it, apparently they got too close. And it was a moment when that volcano released a massive amount of carbon dioxide bubbles. And you are well aware that ships are perfectly designed to float on water, but not on CO2 bubbles. And the last that was ever seen of that ship was the wooden name tag that apparently did come off and float to the surface. So underwater volcanoes are nothing to mess around with, especially if they're explosive and they're relatively shallow, and you don't know what you're doing. Now, our backyard plate, just to reintroduce you to it, it's a simple thing. It used to be much, much bigger, but it's slowly being shoved under North America. Oh, North America is overriding it, actually. And you know that the Cascade Volcanic Range, which is that wrinkle here, those are all produced as a result of this plate pushing beneath this. This is the contact, so that's the edge of the continent. This is the coastline here, and then the continental shelf is relatively narrow here. It's 40 to 60 kilometers wide, and then the plate plunges beneath there, and what you're seeing all along here, those lumps, are chunks of sediment that were on the plate that have been scraped off by the fact that it's plunging beneath North America and leaving behind part of its sediment load, much like snow collects in the front of a snowplow. And so there's an entire story there as well, which we won't go too far into. I'll show you one of the interesting wrinkles of that phenomenon here in just a little bit. But the Pacific Plate is the grand master of the planet, and it really does, it just dominates pretty much everything. By the time it gets to the Western Pacific, it's just as new here by the F of Juan de Fuca as is the Juan de Fuca tectonic plate. When the Juan de Fuca plate subducts, it's sort of leathery. It's not very thick. It's not very hard. And it's only maybe 30 or 40. The plate, now not the crust. The plate is only about 30, 40 kilometers thick. And so it's kind of subducts somewhat gently compared to the Pacific Plate, which is quite thick. And when it subducts, it creates loud booms, magnitude 9s, as does ours, by the way. So just to give you a peek under the rug, let's take a look at it. You see the spreading centers in orange. That's where the plates pull apart at about the speed your fingernails grow. In this case, 6 centimeters a year. The subduction zone I just described to you, and you see those wrinkles there are partly sediment that's been scraped off, but it's also been operated on by erosion from the continents all along the Western Pacific here. This is in the upper left there, obviously that's Vancouver Island here, the Straits of Juan de Fuca. And then there's a transform fault, which is similar to the San Andreas fault. Watch closely as I turn this plate on its side, and you can see the tectonic plate created near the bubble, the ball of magma, which is represented by the bright orange, rising from the mantle below. And then the plate solidifies with that thin veneer on top is lava, which is about 5 kilometers thick. And then progressively on top of that, there's a thin dusting of sediment near the ridge, and the further off the ridge it gets, because that part of the plate is older and older and older, there's more and more sediment, and that's what gets scraped off, okay? So that's the basic form of volcanism on the planet, and seamounts are the other basic form. And here's the way the whole thing kind of works. Beneath the heat source, where the magma chamber is down below, the crustal part here is not very thick. It's only about, as I said, 5 kilometers. And then there's a layer up here that's quite brittle, and it's got lava that's flowed out onto the seafloor. Down here you have what we call magma that's solidified a relatively long period of time. So it's coarse-grained basalt, which we call gabbro. You won't have to remember that. But the heat down here causes any water that's in the system to rise like a hot air balloon, and that, of course, creates a low pressure zone, which draws cold water down and in. Down and in. So it's, as long as there's heat there, and there's been heat there sort of far back as 200 million years anyway to create the oceanic crust in the Pacific. As long as that's been going on, this circulation has taken place, broadly speaking. But that's a generalization, and we will look at that in a little more detail. Now, right up near the top, the fluids that come out have dissolved the oceanic crust, and they have taken some of the gas from the magma, which is constantly burbling off bubbles. And so what comes out here is modified seawater, and I'll talk with you more about that. That modified seawater has dissolved components from the crust, and it also has gases that have come out of the magma. Well, it turns out those components and that gas support a luxuriant microbial community, which has any number, a huge number, of multicellular organisms that live off of it. And this was one of our great surprises, so we'll talk about that in just a bit. I showed you this, so I'm not going to beat on the seamounts again, but you have a similar circulation system. It's just not nearly as vigorous. So let's talk about discovery. How did this happen? And it so happens I have a picture of the 3 dudes that were really basically responsible. In 1977, Jack Diamond, Jack Corliss, and John Edmund got together on a proposal, and they proposed to dive on the Galapagos spreading center, which is east and north of the Galapagos Islands, because there were a few what we call anomalies. There were people like Fred Spiess had towed his sensor package there and found slightly high temperatures, like 2 to 4 thousandths of a degree above what it ought to be. And others had picked up whiffs of something else. And anyway, so they dove. Before they dove, folks like Bob Ballard brought his camera in, and others had other towed packages. It was kind of crude in those days. But they got a picture or two of the odd clam. And so Jack Corliss and a pilot and another scientist dove, and they found gigantic clams. And here's Jack kind of celebrating that you can see these clams are almost the size of Frisbees. And, you know, for about 15 years, Jack, he was loquacious to begin with, but he just would not shut up. I mean, he talked and talked and talked and talked. I mean, I understand he gave lectures that lasted 2 hours. So now, in the interval, I mean, we found that. I won't say it was not an accident, but it was not planned. Let me just say this. When they went out there, all they had on board was geologists. They didn't have a biologist on the entire ship. And so they found these things, and they were preserving them in bottles of alcohol. But the way we discover these things now is called a Toyo, and there's a CTD, is conductivity, temperature, and depth. There's a package, there's a rosette there on the left with a bunch of bottles, but in the middle is a delicate sensor that can tell you how deep you are. It's a pressure sensor similar to the kind that Jerry Peros makes. It also has a conductivity measuring device which tells you how much electricity flows between 2 electrodes, and that's proportional to the saltiness of the sea. And then there's a temperature sensor, so conductivity, temperature, depth. And with that, if you move up and down and you add 1 or 2 little things that look at how turbid the water is, you can get patterns like the one over Brothers Volcano, which shows the plumes that are being released by underwater hydrothermal systems. And so when, instead of just seeing a homogeneous layer down to the sea floor, which it should be, in the presence of these underwater hydrothermal systems, you get these plumes that rise to neutral buoyancy, just like the flat head of a thunderhead, you know, the anvil head of a thunderhead rises to its neutral buoyancy, and then it spreads horizontally. Same thing happens underwater here, except it's full of fragments. So this, in pursuing this approach, we have been very fortunate. This is a map that was compiled by Deb Kelly, and it has well over 300 sites that have been discovered since '77. So we're getting better and better and better at doing this. I don't think all of them have been visited and sampled at the level of the ones that I will talk with you about that we've been studying offshore here. But they have been located, and you'll see they're in every ocean. And so not surprisingly, there are more along the equator than there are in the southern and northern hemisphere. And partly that's because the weather's so bad at high latitudes that most of these hydrothermal people are fair weather sailors, I would guess, except those that study in the Pacific Northwest off the Juan de Fuca area. But you can be assured that down at the southern tip of South America, there's a loop and a little plate there. And the South Sandwich Islands right here, this whole area hasn't been fully explored, and it's going to be loaded. They're everywhere. They really are everywhere. And it's very, very powerful to know how frequently they're found. Now, almost all of them are very similar. There's hot water, low salinity, low pH, that is, they're fairly acid, kind of like vinegar, except 300-degree vinegar. And it's pretty corrosive stuff. And when it comes out, it deposits copper, lead, zinc, sulfides, and animals can live off of the chemicals there. But then, early this last decade, there was a discovery called lost city. Deb Kelly was the chief scientist on the cruise. Now, what I want to point out to you is it's actually fairly important. The spreading center, the Midocean Ridge, the Mid-Atlantic Ridge, is right through here. So that's where you would expect to find the hot venting. Well, this was not actually hot venting. It was relatively cool, and it was up on the top of this mountain, which dwarfs, certainly dwarfs Mount Rainier. It's huge. The seafloor down here is about 6,000 meters, and this is what, Debbie, 700 meters up here? So it's a huge mountain. And lo and behold, that's what the top of the mountain looks like. It's kind of a flat-topped mountain there. And then there are limestone deposits there that are forming from the fluids that are rising from beneath the seafloor. And they're coming from chunks of what we call the mantle. It's not basalt underneath it, it's mantle. And it's made up of olivine or peridot. You may be familiar. You probably have rings and jewelry with peridot. But that's a cutaway crust, and there's warm water, not hot water really. It's about 90 degrees max coming out, and this is what these things look like. And this is a unique discovery. We found nothing else like it, although many of us suspect and are willing to take the bet that there are a number of these and that they are quite profound. We'll talk more about that next week. So, an unusual, after 300 of these things, well, by then it was about 227, but this one was quite remarkable and remains so and has been studied by a number of folks. Two things I want to just remind you of. Photosynthesis is something you're all familiar with. It's what requires you to cut your grass and trim your hedges and all that. And it's basically a process used by plants to convert light energy, normally from the sun, into chemical energy that can be later released to fuel the activities of a particular organism or growth, whatever it is. Chemosynthesis is using the chemical energy generated, in this case, by systems below the sea floor, which produce solutions that have lots of dissolved chemicals from the oceanic crust in it, particularly iron and manganese and things like that. And the energy from those can be used by microbes. The oxidation reduction potential between those elements can be used to produce energy for life. And that's what chemosynthesis is. And it happens in these systems without any help from sunlight, with one exception, and that is that the ocean now, for the last 2 billion years, I don't know if you track things on billion-year level, but if you do, the last 2 billion years, the ocean and the atmosphere have been fairly oxygen-rich, well, progressively more and more oxygen-rich. So, so the deep ocean has a fair amount of oxygen in it. So when these fluids that have been in equilibrium with the rocks and come up, they're what we call reducing fluids. They don't have much oxygen, free oxygen in them. When they come up and mix with the oxygen and the cold oxygen, the hot reducing fluids mixed with the cold oxygenated ocean, the metals drop out. That's one thing. But the microbes have a field day. And then all the animals down there have learned, some of them learn to house the microbes in their body. And the microbes are what they call endosymbionts. The microbe does its thing, and the animal cycles hydrothermal fluid to it. And together they seem to be very happy. Okay, so hydrothermal vent systems, I'm going to just, it's kind of it's not quite a random walk. I'm going to go through a number of characteristics and sort of show you what a hydrothermal system looks like. I'm going to talk about the Endeavour first, and I showed you this before, but this is what the Pacific Northwest looks like in terms of cabled observatory capability. The northern loop is the one that the Canadians have built, and the two southern lines there coming out of near Portland come all the way across the plate, and you'll see the big blue arrow is the eastern boundary current, which I discussed with you before, and it also crosses the entire tectonic plate. So we have the opportunity to make observations, broadly speaking. Now, in the Endeavour, this is a spreading center, and that little white line that you see there is right down the axis of the spreading center. And you can actually see that the volcano is elongate and it has begun to split. There's a weird little volcano on the west side there, but to the lower part here this is the east, and that little volcano is a cute little thing, and it's half cut away by it used to be bigger, and the spreading along this axis has pulled it apart. And that is where the hydrothermal activity is, and folks from here at the university have been studying that area for 35 years. That is the area that Neptune, Canada, it's in Canadian waters, that's the area that Neptune, Canada decided to put their cable to. So we don't work there as much as we used to, but we spent a lot of time there, as you will see in just a little bit. And some studies have been done. A number of us from the UW, and this was something that was published by Deborah Kelly in a recent journal, this cross-section. And it's a seismic cross-section, so what you're seeing is reflections off of layers in the crust. This is the surface of the seafloor here, and it's right along here is where that is. So that's like a cross-section. You have to just mentally assume that it's in position here and it's vertical. The drawings are something that we added, but I want to point to these dots here. Every single one of those is a hydrothermal site. It's the size of the stadium, and it's got hot water coming out. And in between, there's not so much. So we assume that there are what we call hydrothermal circulation cells, where there's cool water that goes down, gets heated, and on both sides, and for one reason or another, comes up here, and it's been consistently doing that. So what these cells correlate to are our guess of what the circulation below the surface is. That's the tricky part. We don't yet have a really good way of looking below the surface of the sea floor, including drilling if we wanted to look at things like this. But we have not let that stop us. We have used our imagination. Oh, before I go to imagination, this is our favorite hydrothermal field. We named all of these. Salou was named by Veronique Robigoux. I think Debbie named Cathedral. I named Extinct Field because I felt I identified with it. They all have different names: Grotto, Lobo, Dante. You know, it's not elegant, but it works. Anyway, every single one of those is a fairly large structure with very hot water coming through it, and it's got animals all over it. And some of them have gigantic, massive deposits of this type of thing. I mean, but they're the size of Volkswagen and wet buses. That's how big some of these things are. And the largest structure that we ever found was a little north of here. It was called Godzilla, and Veronique published a paper on that, and it was 45 meters tall until it fell down, and that was really a very sad time for her because she went to look at it on one of our field trips or our field programs, and it just wasn't there. Well, an earthquake had apparently knocked it down. 2 years later, it had mostly grown back. So these things are big. These are really interesting things. All right, so we're going to look at this field. The one you're looking at here is that dot. You remember the line of dots. Okay, we'll go through that. Now, this is something that Mark Stormer has worked with Deb and others to put together. So it kind of explained the water starts here, seawater, around 2 degrees centigrade and begins to come down. It comes down into here, and it loses calcium and sulfate and magnesium to the rock. And then it begins to get hotter and hotter, and it begins to dissolve sodium, calcium, and potassium. And it picks up copper, zinc, iron, and sulfur. And it gets down into this zone right above the magma chamber, where it's around, it can be as much as 400 degrees centigrade. It's hot. And then it rises because it really is very buoyant at that point. And the upflow zone is, we think, relatively vertical. We don't know. And then there's, in the black smoker region right up here, you get directly venting plumes. And often, as I say, they're over 300 degrees. But that temperature only applies here. By the time they get up here, they've mixed with seawater and they're much, much cooler. And then there are other zones where there's recharge as well. So let's go in and look at that whole picture, and you begin to get a sense of the complexity of what happens. And part of the complexity is what the rock looks like underneath. And part of the complexity is where the magma is down below. And part of the biggest unknown is what does it look like? I mean, you probably spend a lot of time worrying about this yourselves. I do. Is what does it look like right at the interface between molten rock basalt, 1200 degrees centigrade, and cracked rock at 400 or 500 degrees centigrade? What's that boundary look like? And how does it change through time? We know it does because volcanoes erupt. We know it does because some of these hydrothermal systems are vigorous, and sometimes they're just not so vigorous. All right, well, what does it look like if we were to take a giant knife and cut the seafloor out and pull it up like we, plugging a wedding cake or something? You just cut out the middle, pull the piece out of the middle. Well, we tried that. This is actually what I just showed you. This is the area where all those vents were. Okay, so we took liberties with imagination. I mean, that's how you move forward, and then you try to test it. We took liberties, but there's the molten part is down here. We think there are, we don't know what anchors these things, because these deposits up here have been building up for a long, long time. There's a lot of metal out there. We do think that the water comes down peripherally here. So we think it looks something like, if we were to draw diagrams, the diagrams might, or the arrows might look like this. And then the hot water, for reasons we don't quite understand, seems to be localized here for some time. And you would think that that would depress the magma chamber and it would get cold and brittle here, but we don't see that yet. So here's the downflow, and then here's the upflow. And you can see we've depicted the venting with the black smokers coming out the top. So and these really are black smokers at exactly these locations. So we've tried to figure out what it might look like. How do we test it? Don't know. But there's some young people in the audience. Claire Knox, you're going to figure this out, right? Sometime in the future. I mean, that's one of the things you have to leave behind are problems, right? And believe me, our generation is leaving a lot of problems. These are good intellectual problems. And this is what one of these things looks like. And let's look at it in more detail. This is done by Mitchell Ayland. And the whole thing, you really get a sense of the complexity of one of these deposits where out the top is coming really, really hot water, which is already forming black smoke, which are particles of chalcopyrite and pyrite and sphalerite and things like that, which are both iron sulfides and zinc sulfides. But you can also see there's quite a bit of life that basically clings to this area and can make a living from the heat and the chemicals. All right, so you're beginning to get a little bit of a feel. I wanted to point out that Sully, one of the vents that we've studied for quite some time, is not necessarily a steady state anything. In 2000, we definitely measured 380 degrees centigrade coming out of it, which was a surprise. By 2004, it was 360. By 2005, it was 256. Now, we don't quite know what happened, but earthquakes could cause the plumbing beneath the surface to cave in that area. And then in 2007, it was consistently at 230. So these are things we don't understand, but we are making observations and trying to put things together. Now, I want to just show you, and I probably won't talk too much through this, I just want to show you what fin, and you're going to meet fin again. In fact, this is a piece of fin. The sulfide structure named fin had this kind of garment on when we first met fin. And these are the round pebble-like things are limpids. These things with hydra heads are palm worms. They can withstand very, very high temperatures. The tubeworms here with the bushes are plumes are really interesting creatures. They have no gut, no mouth, no anus, and they basically have a trophosome, which is the lining of the body cavity, and it is host to endosymbionts. And the tubeworm just cycles fluid using the plume, which is kind of like a gill structure, down into the trophosome, and the microbes actually can use the chemicals that are in the fluid that are available, and they can make a living. And then the tubeworm, when it's, I don't know if you can call a tubeworm hungry, but when they need to, they absorb some of the microbes that are flourishing in that environment. So it's a symbiotic relationship. We don't quite know when or how the microbes actually enter the young tubeworms, and we don't quite know. We're knowing more and more as we go how tubeworms move, or the early stages of tubeworms move from one place to another. They're wafted in many different ways. But there are still some questions about how these animals work. But I just wanted you to see what this environment looks like. So I'm going to show you something, a little bit of mayhem. I know this lecture is getting a little boring. So you see the fuzzy little creature there, right there? You should come up with a name for him because he's about to take a bite. You see the tubeworm that's its mouth, right there. This is his other end. And he's I don't know, it's dressed up in a fur coat. I don't know. All right, you see, that tubeworm is not paying attention because usually they withdraw. Okay, so I'm going to let that go. But you got to watch it really closely. Watch. Watch. There. It took the whole plume. And it didn't even burp. I mean, I don't know how this is really a weird, I wouldn't want to live here. This is probably worse than Philadelphia. I'm doing it backwards now, so don't think that I'm doing it forwards. But now later, you see that? Later, the tubeworm is kind of dazed, I think. But as time goes on, the tubeworm will stick its little stub out in the hope of, I don't know, maybe growing something else or chatting with this thing and getting its plume back. I don't know. But it's I won't say it's a dog eat dog, but it's a scale worm eats tubeworm. And it's we didn't even know these existed in 1976. Okay. There are some other things, curious little units. This one is Kahihirsuta. You imagine what hirsuta comes from. It's hairy legs, and it has learned to grow microbial colonies on its hairy legs, which it grooms itself and eats. So it's kind of a walking garden. These little blind creatures just lie around in puddles and eat. And I don't quite understand how. They were discovered near Eastern Island. We don't see them in lots of other places. And they are still a mystery. That's part of a black smoker chimney right there. So these things are living right close to the edge. These beautiful plumes, these are the ones that are in the both Galapagos and in 9 North, all along the East Pacific Rise from Baja California down past the equator. Debbie told me earlier that the pink dudes are known as poutfish. Just wanted to show you how densely some of these areas are populated. And it used to be that people thought that seafloor was virtually unpopulated. Now here's another kind of dance, I guess. These are 2 spider crabs. And the minute you put this is a lamppost we were using to take some photographs down there a number of years ago. And that one in the back right here and this one, we don't know if they're discussing what to do with this or what. We do know that when we put something on the seafloor, it doesn't last very long before 2 or 3 of these things will crawl up on it and crawl all around it. And they seem to pick up on vibrations or smell or something. We don't know, but they definitely will come over, particularly around hydrothermal systems where they're very dense. You put something down there, and they'll show up in the neighborhood and they'll look it over. And they will talk to each other too. I wanted to point out one other thing. And you may not have noticed it, but I want to bring it to your attention because you need to be more observant as an audience. Look at the joints. We all have problems with our joints. But do you have these little creatures living on your joints? Look at that. We'll come in closer, I think. And all of them, yeah, see there? Check your knees when you get home tonight. It's an interesting world. Everything is a substrate for everybody else in the neighborhood. Now, the other side of the ocean and that back bay I talked about, the Atlantic, there's a lot of shrimp. Now, remember what you're looking at here. You don't see it probably as clearly as you could. These are black smoker chimneys. So these things are swarming all over, and they're blind. But in their carapace, they have rhodopsin, which is a photoreceptor that allows at wavelengths that are close enough that they can pick up the heat, and they can use that to home in on hydrothermal sites. And they swarm everywhere, and if you look at their guts, they're full of sulfide particles, and the sulfide particles, if you look carefully at them, have microbes on them, and they pass the sulfide, but some of the microbes stay. So here's something that's eating fool's gold for the microbial dipping sauce of microbes, I guess. I don't know how you would phrase it. And then, of course, there are mussels down in through here and one of those fish. So the communities are different. I just wanted to give you a sense of the difference. Now, this is something that our colleague Nancy Penrose put together, and it is a beautiful picture, a video of an octopus, which is a white octopus. They call him Dumbo, but it's really Grimpoteuthis bathanectus. That you have to remember. And Nancy put it to music, but these are the top predator in most hydrothermal fields. And there's a sad story. They don't live very long, 2-3 years maybe, and of course they don't see sunlight, so they don't. But they go through a cycle and they lay their eggs. And they're very protective of their eggs, so they will go to a rocky outcrop anywhere and lay their eggs, and then they will stay with their eggs, and you can hardly get them away. You don't want me to go on, do you? All right, I won't. But we picked up our seismometer anyway, and we couldn't get this. We couldn't get the octopus off until we got it all the way to the surface and were about to load it on the ship, and all of a sudden she jumped off, and we realized that she was protecting egg cases that were adhering to the seismometer. I was distressed, but the biologists were delighted. I don't know if you noticed the eye. It's hard to imagine that they're not intelligent when you look at the eye. It just looks like a giant brain in a way. But this is what it's like on the seafloor. These are or near the seafloor. These are the predators. Those are fins, not ears, although it has been called a Dumbo octopus. So can we hear from Nancy what she put together? Now this one I want to dedicate to my buddy in the audience, Doug Luther. This is a puddle, and we're looking up at it. It's a puddle of really hot water. It's around 300 degrees centigrade. And there's an overhanging ledge, and it's caught underneath the ledge, just like a bubble can be caught under ice, I guess, in the Arctic, Antarctic. But this is hot water. It's around 300 degrees. The surrounding water, in this case, we're at about 2,300 meters depth, 2.3 kilometers. But this is an overhanging ledge, and the flow here isn't as much as it used to be, but there's a water line, and sometimes the flow is greater and it overflows, and when it overflows, it builds more metal deposits out here, and we call them flanges, and they grow, and they grow, and they grow, and they grow, until they're so big they fall off, and that's actually what happened on part of Godzilla when it fell down. It had gigantic flanges. You could park a submarine under the Alvin, rather. So anyway, you can see reflection there. Here's one that Deb and her colleagues photographed in Lost City. And this is the same phenomenon, warmish water flowing out and over the edge, and the flange will grow. And so you're looking up at it from below, and you can see some of the ripples. But it was kind of cool to see this. And the reason that I mentioned it to Doug Luther is that imagine calculating what the gradient is at the interface between 2.3 degrees centigrade seawater here and 320 degree seawater or vent water there. It's a mirror surface. So it's a pretty steep gradient. You don't get natural gradients like that very often. And it always struck me that it would be fun to do experiments in and out of that thing. And bubbles. You don't expect bubbles in the deep ocean. Well, maybe you think about them as being there, but they generally are not because there's so much pressure. You know very well that most of the CO2 that bubbles out of your champagne or your ginger ale or whatever you drink is under pressure, and so that when you pop the top off the bottle or take the cork out, a lot of the gas comes out. Well, the same is true in the ocean. The deeper you are, the more gas can be dissolved in the water, and so we generally don't have much in the way of gas. But when we do have gas, it's pretty interesting coming out of the seafloor. And here's a volcano that has bubbles, and I think you can see them over here, and they're bubbles of liquid CO2 coming out of this volcano. It's the ones I mentioned before, the Japanese ship. This is further up, this gets a little dangerous. You see a better shot of them there. Now, again, the chemistry, and don't go too much into this, but just give you a sense of the difference between seawater, which is in the ocean basins. As a general rule, seawater is fairly constant composition. But the vents are a very different composition. They are all seawater derived. All the water coming out of vents was once in the ocean, and it filters down through the cracks and the pores of the rocks until it gets heated up and then rises. Some of the common black smoker minerals are shown here, and this is a sample. So you see zinc sulfide here. The bright yellow is copper sulfide, and then in other areas up here is pyrite, which is just iron pyrite, just as iron sulfide. And then there's anhydrite, the whitish stuff. And it's simple mineralogy for these sulfide deposits. Here's another really interesting thing that Debbie shared with me earlier today, and it is one of the sulfide structures that Mitch Ayland puts together from mosaics of different pictures. And this thing is, I don't know, about 8 meters tall. But in some of the samples, you can see tubeworms that have been fossilized. The sulfide grows right over them, and they're fossilized in real time. So you have pyrite tubeworms that are often found in these things, and you can study the process by which the pyritization takes place. Now, I wanted to shift gears a little bit and take you to one other place. This is at the base of the continental slope, or near the base of the continental slope, and look at Hydrate. And I wanted to just show you this because it's pretty stunning. Einstein's grotto is shown here. That's the hole in the bottom of the screen. I mean, the hole in the bottom, in the sea floor, at the bottom of the screen. And it looks kind of boring, except if you're a geologist, you can see the rocks are fairly clean, which means something's happening. They're not occupied by microbial mats, the whitish material is microbial mats. And lo and behold, for reasons we don't understand, the methane bubbles start pouring out in bursts, clearly in bursts. This is something we will be studying with cameras and temperature sensors and gas chromatographs and mass spectrometers. We will be, with the cabled observatory, we will be studying these kinds of systems in order to understand how gas hydrate deposits, which are vast in terms of possible resource, and also vast in terms of injecting methane into the overlying ocean. Methane, as I reminded some of you earlier, there's a burst. There's another one coming. So there are times, now, in another hour, this thing will be dead quiet. We don't get it. It's not on a tidal cycle. We just don't, there's stuff we don't understand. And so you can see the bubbles taking off there. This particular one was studied by Brendan Phillip on one of our undergraduates who has published a paper on it. Now here, look at, this is a little bit later, and look, the microbial mats are not nearly as white, and why not? Because they're covered with fragments of stuff that's been blown out by the bubbles. So this is a geologically evolving, chemically changing system. They're not hot so much as they are buoyant. That's over at the continental shelf. All right, so here's the kind of experiments. I want to talk a little bit about what we might do, and then I will wrap up in probably another 11.9 minutes. I hope you'll give me the latitude to do that. So we're going to home in on axial seamount again. This is a fly-in. And axial seamount had an event take place not long ago. There we are on axial. You see the caldera, which I talked to you about before. And here is the Juan de Fuca plate and the Pacific plate are moving apart from one another. And the caldera, that roughly oblong-shaped piece, is a depression in the middle, and it is right on the spreading center. So the two plates are pulling. Where lava flow is, that's the Juan de Fuca plate. Where April is, that's the Pacific plate. And so that's the volcano that we will be studying. And I want to talk to you a little more about that. There are two kinds of plumes that come out of these things. One is an eruptive plume, this one, and they rise as much as 1,000 meters above the sea floor. The others are the steady state black smoker plumes, which seem to rise up maybe 100 meters, sometimes about 100 to 200 meters above the sea floor, and then they reach neutral buoyancy and they go wafting off in whichever way the current is going. The same is true here, but neutral buoyancy for these big eruptions, these megaplumes we call them, that's about 1,000 meters. So there's a lot of excess buoyancy there coming out of the seafloor. So the rise heights are about 1,000 meters above the seafloor for megaplumes. They're as much as 20 kilometers across, and then they spin up as rotary clouds, and they go wafting off in one direction or another. And they carry with them very unusual microbes in that plume. So those are things we want to study. All right, so we have this remarkable system with the cable on the seafloor, and we will be studying axial really very, very thoroughly. There's axial again from a different perspective, and we're looking up the axis of the Juan de Fuca Ridge. So that's north up there, and you can see the sort of the striae are parallel to the spreading, and the angle of the elongate portion of the caldera is off to the northwest, which is there's another story involved there, which I will not beat you over the head with. This is on the floor of the caldera. That's the caldera wall here. It's about 150 meters high, so it's in shadow. This is the outer surface, and then that's the floor of the caldera. And I mentioned to you before, I showed you this lobe was part of a recent eruption. What you're looking at is very detailed bathymetry of the sea floor. And these lobate features are literally lava flows that are 5 to 10 meters thick, and they flow out and then they freeze. And that's what we're mapping with this really good mapping tools that we have. Now there is the primary node. It's called PN3B, primary node 3B, and it's up on the rim of the caldera, away from the part of the volcano that erupts, and it has a cable running across. Those are cables, and then there's another one up there. Here is what we currently have in place. I think I may have showed this to you before. Here's PN3B, and we have instruments. This is the International District. You'll hear from me about International District again in a minute. And here is ashes over here, which is another vent field right at the base of the caldera wall. Okay, and then there's lava all over the seafloor. So this is what we have in place to do all sorts of the measurements that we want to do on this volcano, both the hydrothermal systems as well as the volcano itself. Here's a close-up of ashes and those little pinnacle-like things. That one right there is called Inferno. It's about 5 meters tall, so 2.5 times as high as I am. This is a mosaic that Mitch put together. And every time there's a crack, there's fluids coming up through the cracks of the fresh lava. And microbes make a living wherever they can. And as long as there's warm fluid coming out, the microbes will line the fractures. So that's what you're seeing. And to give you a sense of these things, here is one called El Guapo. El Guapo means the handsome one. And this is a sulfide structure, and it's 60 feet tall. And I'm going to take you from the bottom to the top. Look at the complexity. It was obviously occupied, is still occupied by some living macrofauna, and it's loaded inside with microfauna. And it is very complicated. It's grown flanges, they've fallen off. It's grown other little structures. It's really complicated. And don't you think it's handsome? Hey, don't applaud for a sulfide structure. That's gauche. All right, now the top you have seen before, and it changes daily, and this is what it looks like sometimes. And the reason it looks like that, and this I get excited when I talk about this, the reason it looks like that is that the water coming out is boiling. Even at those temperatures, it's like 340 degrees centigrade. And it's boiling water, and the boiling has bubbles, and what you're seeing is the lights from the submarine shining off the bubbles, and then of course the bubbles rise into the colder seawater, and it quenches the bubbles. But you're looking at a boiling submarine hydrothermal system there. I think stuff like that is really cool. Okay, so eruptive events past and future. We're on the home stretch now. Here was the discovery video of the eruption in Axial. This was after the fact. They discovered by looking at one of their instruments that the chain, which had an anchor on it, was covered with fresh lava. That's when they said, oh, we put that out last year. There must have been an eruption. And that was, they went back and looked at the seismic records, and sure enough, Axial erupted on April 6, 2011. Fresh black lava. And that's what the puddle looked like when it flowed out. You can see traces. You see the dark zones here? Those are the fissures. That's where the lava came out. And it spread, obviously, it's like fluid. It spread downhill. The toes of some of these things are 10 meters high. The one almost made it to ashes. It would have wiped ashes out if it had gotten there. Now here's the International District, because I want to come back and show you. That's where El Guapo was, right there. So this is the eruption of 2011. And you would think, well, we can relax. We don't have to worry about eruptions anymore. This is after the fresh lava was out on the seafloor. This is fresh lava 3 months later. So you think life moves in? It sure does. And here is one of the things that Debbie gets so excited about. It's called a snowblower. There's a cavity below the lava that is lined with all sorts of microbes, and we think these cavities go deep and far, and fresh lavas have these all the time. And we think it populates the oceanic crust with microbes at all levels, and we don't know much about that. It's really quite exciting. Now, why am I bringing you in on on the eruption? Because it's over, John, move on. Let's get to the real story. Okay, so here is the center BPR, that's bottom pressure recorder, and that's this one as well. And that's the whole caldera. This is another view of the caldera. All that rough stuff and this lobate thing, that's all lava flows. And down here is the other BPR. And this is a pressure, it's really a depth on the left-hand side from 0 meters to 3.5 meters. And what we're looking at is the level at which the seafloor of the caldera has either gone up or gone down, because that's what volcanoes do. They inflate and they deflate. Okay, so here is the first major event that was caught. They have a little more data here. The seafloor literally fell about 3.4 meters. So I'm roughly 2 meters. So the seafloor fell further in a couple days than 1.5 John Delaney's. And then they went out and checked where the seafloor was again and again and again over the years, and it was inflating again, slowly. And then in 2011, a bottom pressure recorder caught the event of the 2011 eruption. And you can see that the slope of inflation here from 1998 to 2011 was fairly gradual. It was not what you'd call wild excitement, but it was slowly recovering. And then Bill Chadwick and Scott Nooner started making more continuous measurements, and they found that although the slope started out kind of slow, this is after 2011, all of a sudden, about a little over a year and a half ago, it changed from slopes that were similar to this to a slope that is much steeper. Now, one way to explain that is that their instruments are all screwed up. But we recovered them last year, and they looked at them, and there was nothing wrong with them. And they made other measurements that confirmed that this is the case. It looks as if the seafloor is rising at about 4 times, on the seafloor of the caldera, is rising at about 4 times the rate that it was rising before. And we think that there's something cool going to happen soon, and I hope it doesn't burn up all our cables. So with high power and high bandwidth, we can do many things out there, but one of them is to look at the change. And the question posed to me by Kendra Daly long ago was, well, how do these plumes, these volcanic plumes, actually affect the overlying ecosystem dynamics? And I blush to disclose that I hadn't thought much about it, but you can imagine an erupting volcano. There's the ocean just sort of doing its thing. And then when the volcano erupts, you get this huge plume. Well, it must stir up all of the ecosystem. So we have the makings of almost a perfect experiment. The volcanologists are happy, the hydrothermal folks are happy, the microbial folks are happy, the microbes themselves probably die, but there's more nutrients released, and we have the potential here to do an unbelievably unparalleled study. And this was the framework that Kendra and I developed, with the idea that about a 45-kilometer box on top of this system would be a place where all the folks like her could study the water column continuously, whether anything happened or not. That's good science. And the seismologists and the geologists and the fluid chemists and the like could study the volcanic system. We could do it in great detail in some areas. And I showed you some of this before, but I don't think I gave you the intensity and the insight of why we want to be present for the first time ever to see this phenomenon of a volcano erupting under ocean, which is the environment within which life must have evolved on the planet. It certainly did not evolve in Darwin's warm, shallow pond. So we believe that this is a perfectly viable environment, an erupting underwater volcano in which life may have evolved. Now, it's not going to evolve again on this planet because it's The planet is thoroughly contaminated with life. But these kinds of loose use of the linkage contamination with life. But this is how we can prepare, and you've seen this, but I want you to focus on, I'll let you watch the whole thing because I was racing to finish before and I'm racing to finish now. But we have all these sensors that are going to be in place, and you'll see this wonderful vehicle called Sentry, which is moving. You see it moving there on one of its predetermined tracks, and there's another one coming on this little loop right here. It's called Sentry. It was designed and built by folks like Delaney from Woods Hole, and they will be doing milk runs continuously between eruptions, and we will know what this environment looks like really very thoroughly. No place on the planet will be as thoroughly studied because we can control these things from land. And you know, you see that two-legged mooring in the, it just went out of sight. Come back to that eventually. So this is something new that Mark Stormer's son, Nicholas, has put together. It shows the vehicle mapping the seafloor. And lo and behold, without the plumes over it, he has also modeled the formation of a lava flow. So the shape of the seafloor changes in real time, and we might be capable of actually mapping that process as well. Mapping the accretion of the surface of the seafloor, the active process hasn't been done before. But the real excitement is in this event. Watch this going right now. So this plume, massive amounts of extraordinarily hot water mixing with colder seawater and reaching neutral buoyancy, spreading laterally and being acted upon by the tides. But all of the heat, all of the chemicals, and all the microbes that have come out of the seafloor are trapped in that plume. They don't dissipate. It's not like an erupting surface volcano which goes to the stratosphere, 30,000 feet high, and is wafted away before anybody could ever measure it. Here, we have the opportunity to truly quantify what these kinds of systems are. I'm really very excited about this. All right, this is the downhill pull then. What are the origins of life? What are the limits of life? Those are the kinds of things we're confronting. Here is, I've showed you this before, this is in Mothra. It's the area that we had photographed in every direction, and we have a detailed map of it. And here we have a frame, aluminum frame, but it's got steel wires on it, which is around that sulfide pillar, which we used. And I've got a video clip now here from a NOVA documentary that they did while we were out there. And there's a story behind this. We were running out of time, and usually what we did was use a chainsaw to cut these things. Well, the first time anyway, we cut it with a chainsaw before we tried pulling on it from the surface. You can only pull up to about 30,000 pounds, and then the ship starts going underwater, or the crane on the ship begins to break. So, as we were running out of time, I said to the engineer, Lee Olson from the Applied Physics Lab, I said, Lee, look, I know a lot about rocks, and I can tell that these rocks are not very strong in tension. They have horizontal cracks in them. Let's not cut this one. Let's just go in and get it. We'll rig it, but let's not use the chainsaw, because that was another, it took about eight hours to get the chainsaw down there to use the chainsaw, you know, cut through it, bring it back to the surface, and then go back. So instead, he reluctantly agreed to do it, and it was a matter of some tension, and that's where this thing starts. Lee and I are inside the ship discussing what to do, because we're at 30,000 pounds tension and something is going to break. All right, so this is how it was done normally when Delaney wasn't trying to save time and show off that he knew a lot about rocks. So the cage is put down. There is a one-way belt buckle on this cable that allows you to pull it tight. The chainsaw actually is a hydraulic chainsaw. We have a leftover copy of it, or we have an extra one if you'd like to borrow it sometime. The cut is done, and then it's rigged to this line, which is 60,000-pound test line, which is neutrally buoyant, and it floats to the surface. That's what you see in the lower left, and that's what you saw in the last video. Now, the one thing I wanted to show you, that's Lee in the yellow hat down below. You saw another version of that. But now, what's interesting is on the far right side, well, let's see. The cage, you can see where the cage is on the middle figure, and that's the part, the saw cut was just below the cage. And if you look closely, you can see here, this little square piece here is that little square piece there. Okay, so that's the cut. And what is really interesting is what happened here. That piece, that's where the cut was, and 2 meters of rock grew back in about 3 days. We were surprised. We didn't anticipate that. And some of the highest temperature microbes have ever been cultured, 121 degrees, published by Kashefi et al., was published as a result of this work. So we found some cool things. And we also went to the American Museum of Natural History, and we donated this unit. Well, they actually donated $2 million to the cruise, so we didn't exactly donate it. But you got to make a living somehow. And this is what, you can see the bright orange reflectance is chalcopyrite. And this rock here is from that piece, the one that's on. So that's what you're looking at here in the room. And if you ever get to the American Museum of Natural History, this is in the Hall of the Planet Earth. Now, here are the pieces, and Diane Nielsen, one of Debbie's students, actually did a study of the system, and it shows roughly what we think the whole thing looked like on the upper right. I won't go into that too much because we're racing to get finished. But I wanted to just put one more little anecdote on your plate, which is sort of an elegant step. This is what we think the wall looks like. With the red is 350-degree fluids. On the left, blue is cold seawater, 2 degrees centigrade. And there are gradients through that wall. And we don't know quite what those gradients are exactly. But we decided that was, after we did this, we decided that was something for us to go after. And Deb Kelly wrote the proposal that got oh, sorry. I'll show you this and then we'll go to that. This is what fin, which you're looking at a piece of original fin here, and fin grew this, in 3 days, grew what's on the far left there. But over the years, as we went back to fin, this is what fin looked like as it filled out. So and you can see the bar scale on the right. It's grown over six meters by 2007. God knows what it is now, but it's really pretty interesting. So we went back to this figure, diagrammed it like this. This was part of the proposal that went in, and hypothesized that we would be able to go through the chimney wall with a drill string, which we did, and put an incubator with isolated chambers in it. This has 4 chambers, but the inner side is 300 degrees and the outer side is 100 degrees. And it goes right into the high temperature venting. And the electronics is on the right-hand side. And here it is actually in place in Rowan, with the electronics on the top. And this is work that Debbie has worked up. And you see on the far left is when it was inserted in 2003, June 20. The temperatures rise quickly in the outer chamber. They rise even more rapidly in the middle chamber. And on the inner chamber, it's almost immediately at maximum temperature. And all those events we think are cracking events or something, the zigzag pattern or changes in the temperature as a result of fracturing of the vent. But what's most important are the microbial cells in the chambers. And Debbie found cells in each chamber, and they did not leak from one to the other. That lets you begin to imagine that life may exist at temperatures well above 100 degrees centigrade. Some folks are willing to push that further. All I'm willing to say is, at this point, we don't know what the upper limits of life are. And that is one of the really fascinating things. Debbie prepared this for me to share with you. Microbes live throughout the chimney walls at all temperatures. There are very high concentrations locally, lots of them in a tiny piece of sulfide. The highest diversity is in the outer zones where almost anything goes. Using staining and imaging, it hints that the life may actually be at temperatures greater than 150 centigrade. And some of the organisms the zones are preferentially enriched in a very genetically ancient kind of archaea, which are the ancient kind of microbes, very primitive kinds of microbes. And the next step, according to Deb, is to attach the cable, inject labeled carbon, isotopically labeled carbon, and use a mass spectrometer coupled with a gas chromatograph to look at information on what the metabolism is at the different levels in this thing. So you see we're moving toward more and more sophisticated and rather directed experiments that get at what is the limit to life, and someday we will grow into the questions as Rainer Rilke said. We will eventually grow into, we don't know how to take the answers now, but we will grow into the questions as we grow old. So that's it, and I took a colleague of mine, Michael Collier, to the seafloor in a submarine back in 1991. I figured lots of geologists and scientists had been there and very few poets. And he wrote a poem about that experience, and I'd like to share that with you here. It's called Fathom and League, and it's by Michael Collier, who was the poet laureate for Maryland and is the sixth in line after Robert Frost as the director of the Breadloaf Writers Conference at Middlebury College. He's an interesting human. The background here is the image we showed earlier. That's the Endeavour hydrothermal site, and that's actually one of the sulfide structures that we saw earlier. Where is it? Right there. That's one of the ones that was black smoker, and that's where Michael dove in the submersible. "2 miles down, the seafloor is a skull, the wounded head of a monster, fractured, faulted, ridged. It won't make me think of the earth as mother or understand Gaia, but that my heart is inside my body, and neutral buoyancy is good. How else can the world be studied? But if life begins in the ocean, it thrives on hot and cold in the tumble and boil of the sea, no longer silent. In Genesis, there's no happiness, only awe and improbability. The hideous is beautiful. Worms 10 feet long, clams the size of frisbees, and shrimp that swarm like insects. And something else, water, burning inside water, smoking spires and chimneys. And here and there, to calibrate and measure, a weighted buoy, a probe, or camera I'm coming to retrieve. The sonar pings as if it had an ear to my heart. The echo coming back goes through and doesn't stop until it dissipates, a question formed of sound, empty of the shapes it failed to find beyond the submarine's perimeter of light. Now, at the site of the world's making and unmaking, the way to stay intact is to remain inside the sphere, as if it were a choice I'd made to define myself, but it's no choice. The hatch is held in place by the weight of 300 atmospheres, sky upon sky. There's no courage in this safety, no danger in this passing. The data siphoned, the vents named Godzilla, Hulk, Inferno. My metaphor of monster? The figure of fathom, measuring the depths, holding the unseen, dark, close, hearing in it the sound of its own shape. A name, then a creature, an issue made of what I hold and nothing more. Fathom, the span fingertip to fingertip of an embrace.